Hey there, everybody. Welcome back. This is the second video for 13.8. We're going to be looking at critical points and whether something makes an extrema or saddle points. So 13.8 was on maxima and minima. And last video, we discussed finding critical points. It's when the partial derivatives equal 0 or either or both partial derivatives didn't exist. Okay, so let's take a look at a function you're familiar with. Y equals x cubed has a critical point or an inflection point at 0, 0. It does not have a maximum minimum there. Similar ideas hold true for multivariables. Like notice we didn't have an inflection. This is an inflection point, not a maximum or minimum, but the derivative is 0 there. So let's look at x squared minus y squared. If we look at the two partial derivatives and take a look at what's going on at the origin, the partial with respect to x is 2x, and the partial with respect to y is negative 2y. And this, of course, this graph does not match x squared minus y squared. As we're coming in along, or as we're looking at the partial for both of them, it's 0. So that's good. But take a look at what happens as we approach from different directions. If we approach along the x-axis, the derivative shows that the slope is positive. So it's increasing there. But if we approach along the y-axis, it's decreasing there. Like we come in from y downward, it would be decreasing. So like it's going, like the curve is going up one way, but down along the x, up along the y. This is not good. It does not give us a maximum or minimum. It gives us something called a saddle point. So what we used to check the critical points with was using the second derivative. We checked concavity, the curve, or how much, whether it was concave up or concave down. So at inflection points, the concavity changes, like here. At extrema, the concavity keeps the same sign. When we had a local max, you know, the change or the slope is 0 here, and the slope is 0 here. But the second derivative here is negative. It's f prime of double prime of x is negative. Here, f double prime of x is positive. Concave down, concave up. So that was kind of what's going on right here. Along f of x, the slope was increasing, or it was like, let's see, the slope was increasing. So it was kind of like doing something like that. But for f of y, the slope was decreasing. So it was kind of like that. So we had something like that going on for f of x, y equals x squared minus y squared at 0, 0. It creates a saddle point in 2 dimensions. Let's take a look at a way we can actually find this information with some theorems. So we're going to let f of x, y have continuous second order partial derivatives in some disk around our critical points, x naught, y naught. And we're going to do, it's called the second partial derivative test, or the second partials test. We're going to evaluate the second derivative with respect to x at that point, at the critical point. We're going to multiply by the second derivative with respect to y at that point. And then we'll subtract the square of the mixed partials. So ffx, or fxx times fyy minus fxy squared. So this is going to give us a value. If d is greater than 0, we have a couple things that could happen. If f, or the second derivative with respect to x, is positive, the only way to get d greater than 0 means that the second derivative with respect to y is positive. If they were opposite signs, that would be negative, and we'd have a negative amount. So they both have to have the same sign, and since they are both greater than 0 there, it creates a local min. because it's concave up. Also, if we have d is greater than 0, if f, the second derivative with respect to x, is negative, then the second derivative with y has to be negative also. That's the only way we're going to get a positive d, which means it's concave down there and we have a local max. Then we can look at if d is less than 0. Those are our only way to get maximums and minimums. Those are our maxes and mins. If d is less than 0, we either have one of the two cases. If f of x is greater than 0, then f of y is less than 0, or vice versa. So get our blah blah going on. This creates a saddle point. Okay. If d equals 0, then no conclusion can be drawn. So we'll take a look at some examples in the next video. Keep in mind, this is the important formula right here. This is our second partials test. And we're going to use that. Peace.